Yeah, I think you now should hear us. Welcome to our webinar. If you have any technical issues, let me know. You can use the chat. But now I think we are almost there, so we can start. Yeah, let me start the presentation. So welcome again to our Ceilometer webinar. We are actually in the second session this morning. We already had a number of participants with us, so thank you also to you that we can now have the second session in the afternoon. It will take more or less 30 to 45 minutes. We will try, and then you have still some time for the test. Yes, briefly, if you haven't met us yet, my name is George, and I'm the moderator as well as Holger next to me today. And we will have, as I said, the function, which is the chat function, where you can like raise questions, put comments, because otherwise all other communication channels are on mute. So in order to ensure the quality of the webinar. But if you send us a message via chat, then it should be okay. Yes, to the agenda. We have a technical introduction with the main features of the Ceilometer. Then we go briefly on about installation and communication. But I think you have received all the link to the videos which Holger sent yesterday. So you will have already a good picture, I believe, and then we just do a brief recap. Then we have a part about the data processing and evaluation, especially in regards to the different algorithms of the Ceilometer, and some service instructions. At the end, we have a test and also time for questions. So we did it this morning that we just, please just write down your questions during the webinar, and then at the end we have time to go through it. Otherwise, it will be a bit complicated also with the technical management. Yeah.
Hello again, also from my side. I had also this problem with this very sensitive mouse in the morning, so I will try to move it so much now. So I hope everybody can hear us at least. So it's a must. I don't know if we can check it first of all, maybe.
Yeah, I will just briefly check if you have some questions.
Yeah, somebody said he cannot hear us, but it looks good. So before we talk half an hour and after this time you find out that there's nothing. Okay. So then we start with these key features of the instrument, which everybody should know. So these are, first of all, the output parameters. So the parameters measured by the instrument. Of course, a Ceilometer should deliver the cloud heights. Multiple cloud heights or only the base cloud level. Maybe these are technical differences between instrument classes, but the cloud height or cloud-based delivery is at least a core feature. There are also, for more modern instruments, they also deliver the aerosol layers and a vertical visibility value. These are is also a standard value for this kind of instrument. A little bit more sophisticated is the cloud amount, cloud cover, and other statistical parameters which might be delivered, and also specials like maybe this sky condition index, which is a precipitation or fog index indicating when it's foggy and or when it's starting raining or snowing or whatever. All these parameters inside such a Ceilometer, inside our Ceilometer, are delivered, are calculated within this so-called sky condition algorithm. So the sky condition algorithm is something integrated in the Ceilometer, delivering all these parameters, and maybe some more in the future. There are other many hardware-driven topics, or for example, the sensitivity of the instrument, the laser technology, which are integrated, also the interfaces. So we have these two interfaces. It's the serial interface RS-5.5 duplex mode, and the Ethernet option to directly connect the instrument to LAN, so you can work with the web interface on the instrument and get the data directly. So the housing design, everything, it's done in our way. These are technical data which can be discussed, and sometimes the people want some more features like this, sometimes less. So this depends a little bit on the request from the customers. The laser in the unit is a laser class 1M product, so the full unit is specified as laser class 1M. This is important for airport usage mainly, but also Met services will not integrate a system typically which has a higher laser class. They cannot accept it. Here's just this overview about also the techniques of such a single wavelength. It's a single wavelength because we only send out one wavelength at 1 micron or 1064. Yeah, it's a neodymium base wavelength, and we are using a kind of optical filter to suppress the daylight, have this typical pulse repetition frequency of 5 to 7 kilohertz. And microjoule, there is also a mistake I see, so it's not 8 millijoule, it's 8 microjoule, because we are using a microjoule laser inside our system. I come to the next point for the introduction into the Lidar technique. Also, you must know a bit about the space technique. So even we call our instrument a ceilometer because the focus for the instrument is measuring the ceiling, the base, cloud level. This is still the focus of this instrument class. So Lidar is an acronym for light detection ranging. So it's close to the radar technology. You send out an electromagnetic wave. It is scattered by aerosols, by larger droplets, and also by the molecules in the atmosphere. Part of this light is scattered back and typically collected by a telescope or by a lens, and finally is in the instrument sent out and by a detector. It's measured by a detector. So for this backscattered light, there is, of course, you have always a daylight. So one important thing is how efficient the daylight can be suppressed. And another topic is you see that you send out only a microjoule of a laser pulse, and you have this partly very inefficient scattering processes in the atmosphere and get only a few, less than a percentage. It's a 10 to minus 8, sometimes 10 to minus 6 factor is scattered really back to your unit, and so you need a sensitive detection system. We are using this single photon counting detection system, but also very sensitive analog detection systems are available to measure this low amount of energy. At the bottom line, you see such a so-called Lidar equation. It gives you all the terms which are responsible for the power which you send out and to the power you finally have measured. And in the middle you find a function, it's called the overlap function, O from X and the wavelength. And this function we will look at the next page. So the function looks like for our CHM 15k instrument, like in the upper right corner, you will find the two main reasons why these functions looks like in our case like they are. So one reason is that we have a B-static axial system. So this is on the left side. You can see it on the left side. In principle, you have a region when you send out the laser beam. You have a region where the laser is sent out, but nothing can be collected in the field of view of the detector. And so let's say we are below the X1 level in this moment. So there is no signal at all. Then you have a region until X2 or X3 where not all of the light is collected. So you are in an overlap region from your signal where you have a percentage. You can measure more and more percentage of the total light you send out. Yeah, but not all, still not all. And starting from X3 over X3, we collect all the light which we send out, which is in principle scattered back by the molecules or particles. This is one effect, yeah, leading to a situation that you have at low indexes. Here is the distance scale. This is a kind of intensity scale. So the overlap function have values from 0 to 1 here. And 1 means 100% can be detected in principle, and 0 means almost nothing can be detected in a so-called single scattering process. There is another thing which is also important, or it is especially for single optic systems, for these coaxial systems, the second effect here is even more important. This is when you are in infinity, like with giraffe in this object, in this example. If you are in infinity, then your focal plane after your lens inside your instrument, the image is in a focal plane. But if you come closer with your object, for example, closer than X1, the single optics will not help at all, because your image is far behind your focal plane. So you will not detect 100% of the light, because you are not in the focal plane. And so this effect happens independent if you are in a biaxial or coaxial mode. Yeah. So finally you end up with the overlap function due to such a setup, which always looks like this. And the same would also, if you have a coaxial system, it would also look the same, like the Weissala instruments. Just about the sizes of particles and droplets or molecules which we can detect. So we are saying we have a laser with 1 micron. With 1 micron, we are in the middle of the, let's say, interesting substances which we want to detect. So we have smaller particles, and mainly up to these very small molecules, which can be not detected as efficient. We have a lot of particles like fog, for example, itself. It has exactly the size of 1 micron, 2 micron, 5 microns. So exactly in the size of our wavelengths, so it can be very efficiently detected. And there are larger particles, for example, also some like volcanic ash. Volcanic ash is spread from a few microns to hundreds of microns. Yeah, so you need you can measure it very well with the 1 micron system, but to differentiate now between different particles or different sizes, you need at least 2 or 3 different wavelengths. For example, for full detection of volcanic ash, it helps a lot to have a radar wavelength and a Lidar wavelength and compare these results. So you can get a lot of benefit in combining these two if the particle size is spread over such a range. And if you want to detect very efficiently or more efficiently molecules, then you need a UV wavelength at least. You can see much more because this molecule scattering, or so-called Rayleigh scattering, depends on lambda to -4. Here are 2 results now for the volcanic ash measurements. So these, as I said, the instrument can detect these volcanic ashes due to the size of also these particles. Here is a second from the DW second example. In this case, these are calibrated data where the people used sun photometers to calibrate the data and calculated the extinction coefficient and also the mass concentration within this plume. About the components of the system. So we have this outer case, we have an inner case. There is an airflow between the outer and inner case. It helps us in summertime to cool down the inner housing, in winter time to heat the housing. The cooling effect, we need this fan for the cooling effect, and of course in the upper part you have a laser outlet, so most of you have already seen this instrument. There are inside the instrument, if you open the inner door for service, there are some guiding rails for the so-called laser optical unit, the black unit. So this can be exchanged easily for service or for a new calibration alignment. On the right side, you see this main controller and also a laser controller, and there's a housing heater additionally implemented, which is typically only required below 0 degrees Celsius. Some of these principal function units, you must not know all these things in detail, but for you it's necessary to see that there is a main controller which typically gets all kind of data from the different units, from temperature sensors inside, from the detector itself, from the laser. So all of these statuses from these units are measured and controlled by the main controller. And the modern functionality of these units is they deliver a very high quality status to the end user. So the end user have not the people and the time anymore to look at the instrument quite often. They want that these instruments are self-controlled more or less, and if something happens, like for example the window is dirty or the laser power is getting down, then the end user wants to be informed in general, and this kind of collecting of different information is done by this main controller. On the left side you see also a typically measuring cycle. So in each cycle, all the statuses are measured together with the raw data itself. Yeah. For the installation and communication, of course, you saw hopefully also this installation video to get a more deeper impression about an installation. Yeah. You must check, of course, the instrument delivery There should be the cables. The cables are always included in our instrument. So there's typically 10-meter cables, the screws, some extra paperwork. There's always a drilling plate, part of the delivery. It helps us to install. It helps you to install the instrument and drill the holes in the concrete plate. So then you can more easily go there without the instrument. First of all, prepare the holes, and then you can easily install it. So drilling holes and fixing the instrument carefully, especially at windy places, on roofs, and etc., it's necessary to do. Yeah, so there is some special also for this 230 volt. This was the standard power supply since this up to this year. So next year we will come up with this 110, 115 volt power unit. So far we used always a voltage converter in the past, but there are some regulations that voltage converters cannot always be accepted, for example, for lightning protection. So we decided to come with a really pure 115 volt or 110 volt system in the market. It will be available in up the first quarter in 2016. LAN cable, RS4 cable are always connected. Instead of the LAN cable, sometimes we deliver also the DSL cable if you have just not so powerful communication lines. The communication can be done via RS485. Typically you use a terminal program. There's also a graphical supported terminal like the data client software. Over the Ethernet, it's more the modern version, let's say, to configure an instrument, because you have a web interface where you see all parameters. You must not have to look in the manual as often to find out how the special command looked like, which is sometimes necessary for the RS485. But for the LAN, you easily see it, you have an overview, and you can configure the instrument. A bit more intuitive. So for the RS485, here just an overview for the transfer mode. This is an example how you enter a command. It's always set, done a space. The 16 is our typical RS485 number by default. You can change it, but you must have a really good reason to change it, because in the manual everything is written with 16. It's only necessary if you have really in one line more than one CHM 15k instrument, which is typically not realized. Yeah, for LAN, for the Ethernet LAN connection, since years any of these kind of browsers can be used to access the instrument via LAN. There's one fixed address which is always available for service purposes. It's this 192.168 address. So you can always use this address to enter the web interface to the instrument with a direct connection, I have to add. So you enter, you connect your laptop to the instrument, and you can work with this address. If you are in a DHCP network and you connect the instrument in the DHCP network, there will automatically an address will be signed for the instrument. And if you want to find out this address, you can do it via the RS485 by entering the correct command. It's one idea. If you have not the RS485 connected, you must find out the IP address, for example, by a port scanner. This can be easily done. You will find this information in this one of the videos too. Also, the RS-485 is listed over there. So, and then of course you can access the raw data, for example, or can configure the instrument over the web interface. Here's how it looks like. The configuration on the left side. Location, institution, everything should be filled out carefully to have this information in the header of the raw data files. On the right side, you see the network configuration page. Also you can, there's one fixed address which cannot be changed. One is given by the DHCP server. This can be shut off if it's necessary. And there's also some other options like this AFD. It's a file distribution system and so on. For the data processing, so we started with this already. Here you see a picture, for example, of the CHM viewer software, and this CHM viewer software, is an extra tool available to have a good and closer look at the measured data and the evaluated data of the instrument, to bring both parties together, the raw data and evaluated data. And then can be checked out if the internal processing unit has done a good job or not. So for example, you can click, and one of the checks there to display the Wolkenhöhe, the cloud height. So it is displayed in English if you have an English computer. You can display also the penetration depth, in German called Wolkentiefe, or in this case here you see with these green dots in this color plot, you see the planetary boundary layer, the PBL. So what you see in this picture is on the y-axis the altitude for both graphics, and you see in the color plot, you see the time on the x-axis, and on the other side you see a cut through this, you see the intensity. And on the color plot, the intensity is color-coded. So what you have here with these dots, there's at the lower end, you see that the aerosol layers at the bottom below 2 kilometers, this is a little bit more homogeneous than the noise above. And the edges of these aerosol layers, this planetary boundary layer, these and some structures there are marked with these green dots. So one of the tasks for the sky condition algorithm is to find out with those layers, mark them as aerosol layers, and in further processing steps, they can be identified as mixing layer heights and so on. This is what we have already discussed before. It is these quality indexes. This is all what the sky condition algorithm delivers. So I do step over this. There's also not the sky condition algorithm, the sky condition index, which shows you most of all if there is some precipitation or if there is no precipitation. So this is a little bit coded. It gives you first advice, especially for example, if you cannot measure because the window transmission is absolutely reduced. There are too many droplets on the window, then it's also marked here. Also one measuring example now for this planetary boundary layer, this PBL, which you saw before. Here are examples from France and from Germany too, showing you some structures within this boundary layer to find out where the aerosol concentration is higher and where the aerosol concentration is poor. There are another part of these so-called enhanced or second step algorithms are these cloud cover algorithms. They are always, they are also asked by some of the Met offices, also by the solar industry. They want to have this information. If they're using ceilometers. So here you see all these dots are clouds. You see again this cloud height, and you see the time, and all these dots are some of these dots are clustered to, let's say, a cloud type or cloud which they are combined here to a clustered, let's say, and so there is a statistic over 10 minutes to half an hour or several hours at high altitudes, which comes close to the meteorological observer, and he looks into the sky and decide there are, let's say, 5/8 cloud cover levels. Then the instrument tries to simulate it and do the same job and compare these results. And this comparison, so these results are given in octas or in eighths, let's say, and there are these 0 to 8, of course, and also one it's called 9. It is for a total obscured sky where in principle no real cloud base can be observed, because it goes to the ground. It's a mixture of foggy situation. Here's one comparison result from Germany, from the ANDER, it's from the German Met Service, the system collecting all data. There's different cloud cover to cloud cover algorithms were here compared, and there are ANDER results and the meteorological observer results too. So, and this comparison were done from 2010 mostly and to 2012 to find out the best algorithm for these ceilometers. Another big step was also to getting these vertical visual range values. Typically they are measured in a horizontal way. We have here they are marked in an old picture in Jena city. We are doing these measurements, and when we have some foggy situation, we can use them for good comparisons and to find out if our reference units are still in a good condition or not. Here's just the graphical view, the mathematical procedure, how this is done. So there's the extinction is calculated and the extinction is summed, and then we end up with the estimated and computed results. For service instructions, in principle, the main maintenance you have to do is cleaning glass panels, and maybe also clean the fan intake, and if there are some leaves in autumn, it must be removed. Same as for the glass windows as well. The instrument will deliver always with each protocol. In each file, you see the status of the output window. If it's getting dirty, too dirty, you are getting warned too. Also, one thing which has to be replaced time by time, it's these dehumidifier bag. You can find it in your country too, and can replace it by your own regularly in every few months or once per year. If you are anyway living in a dry area, it can be stay for a year. If you are living in a humid, wet area, maybe 2 months is also a good time to change this back. So you shouldn't wait until there's a lot of liquid inside, because it's a salty liquid, and the back can be destroyed if it's getting too full. There's also an SD card. As I mentioned before, you can exchange the SD card after several years. So it's also an inexpensive exchange. And the laser optic module, which here you see in a picture, this must be exchanged roughly every 3-4 years for new calibration, and maybe it can also survive for 6 years, but there's no warranty for it. So you must calculate every 4 years. You need a recalibration and alignment of these optical black units. And when you do this, you wait typically until the laser diode is close to the end of the lifetime. Okay, so are there any questions? So we stop here with this session. Yeah,